So now that we have covered determinants, minors, cofactor expansions, we finally have the tools we need to tackle something that was actually mentioned way earlier in the course called the cross product. So as a quick reminder, the determinant of a 2 by 2 matrix, if we have a matrix A, B, C, D, we write it with those vertical lines there, and it's just AD minus B times C. So it's just this diagonal minus that diagonal. So if I gave you the matrix C 2, 5, 3, 4, and we want to find the determinant, we would just say it equals 2 times 4 minus 5 times 3. 2 times 4 is 8, minus 5 times 3 is 15. 8 minus 15 is negative 7. And so we would get that determinant. And that's like what we did last time, right? We found the determinants. We also found the minors. So for example, if I have this matrix here and I wanted to find minor 1, 1, if I wanted to find minor 1, 1, all I need to do is remove row 1 and column 1, so I would just be left with 5, 6, 8, 9. Find the determinant here. 5 times 9 is 45. Minus 8 times 6 is, what would that be? That would be 48. And 45 minus 48 is negative 3. I could also do this for row 2 and column 2. I'm going to show you what I'm doing on this matrix for this one. So I'm eliminating row 2 and column 2. And if I were to do that, if I were to find minor 2, 2, I could get that as the determinant of the matrix 1, 3, 7, 9. I know it's kind of weird to think of it that way, but I could cross out the second row and the second column, and I'd be left with those numbers. And if I did that, I would be left with 1 times 9, which is 9, minus 3 times 7, which is 21, and then 9 minus 1 would be negative, what would that be? That would be 20 minus 8. I mean, negative 20. That would be negative 12. The big reason we used this was we could use it to find the determinant of a 3 by 3 matrix. And I'm going to help you with this. I told you there's not a great formula for a 3 by 3, but there actually is one that's like kind of okay. If I were to specifically only evaluate along the first row, remember that it's the element times the cofactor. So this would be A1 times the cofactor of what's left. So if I did the first row, first column, the cofactor for 1, 1 is actually still going to be just a positive number. So it would be the determinant of B2, B3, and then C2, C3. And then if I keep going, I'd be at A2. And here's the interesting thing. At A2, our cofactor would be negative. So instead of putting a plus here, I'm actually just going to put a minus, and then I can just deal with the minor. So if I dealt with the minor here, it would be B1, B3. So it would be B1, B3, and I'd be left with C1, C3. If I keep going, the third element would be A3. Oops, I should close that determinant. I would have A3 times the determinant of, if I block out this column here, I'm left with B1, B2, C1, C2. B1, B2, C1, C2. And this one would be positive because the element in the first row, third column, if I had 1 plus 3, that's 4, which means it's positive. If we were to even go further than this, we actually could multiply this out. It would be, and this is why I told you there's not a nice formula for this, because it's really not that good. I'll have A1 times B2C3, B2C3, minus B3C2, B3C2, close parenthesis, minus A2 times B1C3 minus B3C1 plus A3 times parenthesis B1C2 minus B2C1. This is the actual formula for a 3 by 3 determinant. Yeah, no one memorizes this. No one ever memorizes this, but this is the actual formula. So I'm going to show you what I do, because I don't memorize this whole thing, but I do like this idea of like the plus minus plus thing. So that way I don't have to really worry about cofactors anymore. I can just think of it as minors. So I'm going to expand this along the first row. I'm going to take this idea of just expanding on the first row. So that would be 2 times the determinant of, in this case, 5, -2, 3, 1. Again, what I'm doing there is I'm blocking out all of the first row and all of the first column. All that's left is 5, -2, 3, 1. Minus, and then I bring in the next element, 3, times the determinant of 1, -2, 2, 1, plus 1 times the determinant of what's left of 1, 5, 2, 3. From here, I'm going to find the determinant. 5 times 1 is 5, minus -2 times 3 is -6. I think this is going to work out to positive 11. So I have 2 times 11 minus 3 times, I'm going to figure that one out in a second. 1 times 1 is 1, minus -2 times 2 is -4. 1 minus -4 is 5. So it's going to be a 5 here. Plus 1 times 3 is 3, minus 5 times 2 is 10. I'm getting -7. 2 times 11 is 22. Minus 5 times 3 is -15. And 1 times -7 is -7. And what would that be? -15 minus 7 is -22 plus 22. This whole thing works out to be 0. That wasn't that bad. So you know we gotta make it worse. What if I gave you this determinant right here? What if I gave you this determinant right here that says I have ijk with A1, A2, A3, B1, B2, B3. As a quick reminder, because I know it's been a little while, if the letters are bolded, that means it's a vector. So I'm saying I is equal to the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. I never explicitly said that we could only have numbers inside of a determinant. I told you the answers typically work out to be numbers, but what if I had something inside of there? What if an element wasn't just a number? What if I had a vector? Well, our determinant rules still are the same, right? I'm going to go the first element. I'm going to expand this along the first row. For what we're about to do, I really want to do this first row. I would get I times the determinant of what's left, A2, A3, B2, B3. So I get A2, A3, B2, B3, minus J times, I would have A1, A3, B1, B3, and then plus K times, and then we'd have A1, A2, and B1, B2. That's what that would mean, right? If we had the determinant and I had I, J, and K in there, hey, you know what? Oh, well, there we go. And from there, we could figure out what these determinants are and move forward. Well, what we really just did is known as the cross product. If I have two vectors, let's call them A and B. If I have two vectors, let's call them A and B. If I have two vectors A and B, I can set them up in a matrix like this, where I put I, J, and K along the top, and then I do A1, A2, A3, B1, B2, B3, and then we expand along row 1. This, by definition, is the cross product. This is what the cross product. When we were in vectors and I told you there's the dot product and then there's something else, this is the something else. So if I want to find U cross V, what I need to do is I need to set up the determinant for u and v. My first row is always going to be I, j, k. My first row is always going to be I, j, k. My second row here is now going to be the numbers for u. So it's going to be, if I were to write u as a vector, it would be the vector 3, 2, -1. So the numbers here are going to be 3, 2, -1. If I were to write vector v as a vector, that would be 1, 3, 2. So that'll be the numbers 1, 3, 2. From here, it's a determinant like you've done it before. It's going to be I times the determinant of 2, -1, 3, 2. Because again, I'm expanding along this first row here. So I'm doing the element times the minor minus now the next element, which is going to be j, times the minor, which is 3, -1, 1, 2. Plus k times the minor 3, 2, 1, 3. And from here, we're going to work out these determinants. So I have I times 2 times 2 is 4, minus -1 times 3 is -3, minus j times 3 times 2 is 6, minus -1 times 1 is -1, plus k times 3 times 3 is 9, minus 2 times 1 is 2. I'm left with, this will be 4 minus -3 is 7, so I have 7i. Here I have 6 minus -1 is 7, but there's a negative out front, so it's going to be minus 7j. And now I have 9 minus 2, which is 7, so I have plus 7k. We typically wouldn't leave the answer like this. We typically would write this final answer here in vector notation. We would write it as the vector 7, -7, u cross v would be equal to the vector 7, -7, 7. I know, that's weird. This is a new form of multiplication. We before had the dot product, and if you remember from back then, the dot product was always equal to a number. Well, now we have a way to multiply vectors that gives us another vector. It's so cool. Let's do another one. Now I have v times u. So we just did u times v. I want to try doing v times u. So to do v times u, I'm going to set it up very similarly. I'm still going to put I, j, and k in the top. So I'm going to put I, j, and k. First in this cross product, I need to put vector 2 here. I need to put that one first. So that's going to be 1, 3, 2. So I go 1, 3, 2. And I need to put vector, which would be 3, 2, -1. That's going to be 3, 2, -1. From here, the process is the exact same. I have I times the determinant 3, 2, 2, -1 minus vector j times the determinant of 1, 2, 3, -1 plus vector k times the determinant of 1, 3, 3, 2. And from there, we're going to evaluate these determinants. I have I times 3 times -1 is -3, minus 2 times 2 is 4, minus j times 1 times -1 is -1, 3 times 2 minus 3 times 2 is 6, plus my vector k times 1 times 2 is 2, minus 3 times 3 is 9. If we simplify these, -3 minus 4 is -7, so I have -7i. I have -7i. Here I have -6 minus 1 is -7, but I have a negative out front, so that's going to be plus 7j. And then last but not least, 2 minus 9 is -7, so I get -7k. And again, I wouldn't leave it like this. I would write my final answer as a vector. I would get the vector -7, 7, -7. So that means v cross u is equal to the vector -7, 7, -7. That's cool. Let's try some more. Let's try something else. Let's say I had v cross v. What if I multiplied a vector by itself? What if I took the cross product of a vector by itself? So I'm going to set it up the exact same way. I have I, j, and k. I have my vector v, which I think was 1, 3, 2. And I'm going to write that exact same vector again, 1, 3, 2. So this will become I times, if I block that out, I'm going to have 3, 2, 3, 2, minus j times 1, 2, 1, 2, plus k times, what would that be, 1, 3, 1, 3. And as I'm doing this, I'm noticing something interesting. 3 times 2 is 6, minus 3 times 2 is 6. What? 1 times 2 is 2, minus 1 times 2 is 2, plus k times 1 times 3 is 3, minus 1 times 3 is... All of these work out to 0. All of these work out to 0. I'm going to get 0i minus 0j plus 0k. I'm getting the vector 0, 0, 0, otherwise known as the 0 vector. So that means that I take the cross product of something crossed with itself, it will always give us the 0 vector. If I take the cross product of something crossed with itself, I will always get the 0 vector. But I could take this a step further. Let's say I wanted to take the cross product of u cross v, and don't worry, we already did it, so we're going to just copy that over. And now I want to dot it with u. What if I wanted to do the dot product of a cross product? What if I wanted to take my u cross v, which we just said was 7, -7, 7, and I wanted to dot that with my vector u, which vector u is 3, 2, -1. Well, it's been a while for dot product, but as a reminder, it kind of works like matrix multiplication. We're going to do the first one times the first one, plus the second one times the second, third one times the third one. So I'm going to go 7 times 3, plus -7 times 2, plus 7 times -1. 7 times 3 is 21, minus, minus, because that was -7 times 2 is -14. And 7 times -1 is -7. Well, wait a minute. 21 minus 14 minus... This whole thing works out to 0. It's very interesting. Maybe it's a fluke. Let's try another one. Here I have u cross v dotted with v. So I have u cross v again from over there. 7, -7, 7. So let's say I do 7, -7, 7. And instead of dotting it with u, I want to dot it with v this time. V was the vector 1, 3, 2 off memory. So it's the vector 1, 3, 2. And as I dot this, I'll get 7 times 1, plus -7 times 3, plus 7 times 2. 7 times 1 is 7. Plus -7 times 3 is -21, plus 7 times 2 is 14. Wait, the whole thing's 0 again. The whole thing is 0 again. So my question to you is, what does that mean? So if I look at letters D and E, see how they both turned out to be 0? What does it mean if the dot product is equal to 0? Well, that means they are perpendicular. That means the cross product will always be perpendicular. U cross V is perpendicular. Sorry, it's spelled very badly. Is perpendicular to U and to V. Another way to say it is it's orthogonal to both U and V. That the cross product of U and V is perpendicular. It's the vector that's perpendicular to both u and v. Also, if we look back, what does letter A suggest? When I did u cross v, I got 7, -7, 7. When I did V cross U, I got -7, 7, -7. The numbers are almost exactly the same. The only thing that's different is the signs. So what that means is that U cross V and V cross U are related. They are very similar. U cross V is almost equal to V cross U, right? There's just a little bit difference. V cross U. The only difference is, if I have U cross V and V cross U cross V is equal to -1 times V cross U. It's just equal to the opposite of V cross U. And that's where we're going to stop this. Hope this made sense. We're going to continue this idea in class. Please let me know if you have any questions.